Welcome. First lab tension experiment of EMA or ME307. So here we are with the teaching assistants who guide you through the lab. First things first, we have safety. So Professor and I am selecting safety glasses. Once we have them on, now we are ready to go and begin our experiment.
Safety first.
The first specimen is an A36 steel.
So these are the jaws for the machine. They're very expensive, so don't break them.
Yes, they are $3,000 each. Notice the wedging action. So these can grip a cylindrical specimen, and notice how they will, how the specimen will be under tension once we tighten the grips because of the wedging action of the grips. Okay, so now he's putting the handset in the manual mode so that the control of the crosshead is with the handset and not with the software.
Notice how the crosshair is going up, as you can see in two displays.
Oh, and these are the optical stops. There is one before the crosshead, above the crosshead, and one below the crosshead. If there's an optical sensor on the right side of the crosshead, if the sensor sees the reflective band of the optical sensor, the crosshead's movement will stop. So before every test, we should ensure that the optical sensors are away from the crosshead. And now he is making enough room for the specimen to grip in.
Here we must mention that the grips are designed for round specimen. Jaws have a round profile within, and there he'll fit. So
also notice the shape of the specimen. This is not like a fully cylindrical specimen. This is a dog bone shaped specimen, and I think this is as per the ASTM standards, which is E8.
Yeah. Notice how he doesn't put the sample against the jaws, and there's a little gap on the top. This is so it doesn't damage the jaws when he fully tightens it. So this is very important as to not breaking the jaws.
Oh yes, we should leave a 5mm gap at least so that the jaws do not damage because of the recoil action. Also, let's pause the video here. This is the TestWorks software, and we can see three different output channels. The one on the left side, which is 11.62, is the crosshead displacement in inches. The middle one is the extensometer strain, and that is inch per inch, so it's unitless. And the third one is the load value in pounds. So let's start the video.
And here we have fine adjustments. He is operating the machine in a slow clutch mode so that he can maneuver the control, but then slow clutch will probably take a lot of time, and he just switched it to a high clutch mode. So here you go. But you should be very careful by using the high clutch mode because that might smash the specimen. So be very careful while doing that. Also, make sure that you leave the 5mm gap when you have finished the clutch control.
Also, why did he insert the specimen first in the top jaw and not in the bottom jaw?
This is so that you can cancel out the weight of the specimen using the software, so that the weight of the specimen does not affect the sample.
Oh, so that is why the load cell is the black colored portion, and since it is attached to the top jaw, we need to insert the specimen first in the top jaw. And also he tightened the lower grip, but he did not zero the value of the load, right? Oh, so that is why he is loosening the bottom grip. And now he's right clicking on the load channel and then clicking on zero load value. So from 22 the load goes to 0. So now we have nullified the weight of the specimen.
That's pretty interesting as to start with. And now we're checking the grips for one final time before we roll on and start our test. Are we excited?
Also notice how the value of the load changed when he's tightening the lower grip. Like from 0. Wow, it's changing a lot, right?
Yes.
Also, make sure you don't over tighten the grips. Make sure it's just finger tight, because you can damage the sample if you try to over tighten it.
Oh yes. You're right.
So at this point, we're making final adjustments before we start the test and click on the play button. Well, that's not a play button, that's the start button. What do you think?
Yes.
Yeah,
So we should zero this load, right?
Yes, we should.
we should. But we shouldn't.
But we should not, yes,
Yeah.
because this is the actual load. And before starting the experiment, we saw that he used the handset, the fine mode, to control to bring the load value around 0 to 10 pounds. So now he's clicked on start the test as Dave said, and he entered the sample ID, and now the software is asking for the diameter, the gauge length of the specimen, which Professor Dressler forgot, right?
So we need to start again.
Yes.
Let's start with measuring the specimen.
He should have read the lab manual before performing the experiment.
Yes.
Well, you can see that the vernier caliper is not set at 0, so somebody
there
must
would
have
be-
tampered it.
Well, there would be some freshmen around in the lab.
Yes, they have forgotten to make proper adjustments. So now that it's set, we have started to measure the diameter of the specimen. That's pretty important because we need to know what is the cross-sectional area that is put under tension.
And this cross section is very important. A small change in that value can change the overall actual measurement of the stress by a significant.
Oh,
And
yes.
so the ASTM standard is 0.35 inches for the diameter, and so what was measured was around 0.348, so slightly smaller than the actual diameter.
Oh, so now he's entering the diameter and the gauge length.
So now he's measuring the length of the gauge length with the calipers. Notice how the edges are filleted, and the fillet makes it very hard to measure the exact. So entering these numbers are crucial though. So make sure you have a consistent way of measuring it.
And now he's entering the dimensions. The third one is the gauge length of the extensometer, which is one. We'll learn about that later. And then he clicked on start the test. So the crosshead is moving up, and we can see the value of the load and the crosshead change in the testwork software. The load increases rapidly, right?
It does.
But the length does not change very fast. As you can see, it's about only 0.01 inches per second.
Wow, so the stiffness of the steel specimen is a lot.
Behaves like a very stiff spring. So we can see the value increasing. So from 4,000 to 6,000, it's just taking very little time, and we're about to see a drop for a moment.
So we are in the linear region and a drop. Oh yes, it dropped. So I think this is because of the slipping of the specimen in the jaws. So now it's rising again, so it should be okay.
Yeah, we do face these problems while doing experiments, but that's nothing
Yes.
to worry about.
Yes, in theory, in books, you never see these.
Yeah.
That's why experiments are fun, right?
That's why you're in 307, ain't you? So yes, we are heading north, and of how much? 6,000? 7,000. But we'll see how far it goes. So right now we are at a cross section which hasn't deformed yet. We have turned on our other angle, and you can see clearly how the cross section.
Yes, the deformation is uniform. There's no signs of necking as of now. And
So it is rising up, and I'll bet probably it will reach 7,000 pounds. What do you say?
oh, I feel this will never break. It's at around 7,000 already. The design capacity of the setup is 10,000 pounds. I don't feel this will break. What do you think, Ed?
I think it'll break around 6,900 pounds.
Wow, so just below the Dave's value.
We have just kept it at a certain value, and let's see how far our bet rises. So we are at some 6,600 pounds as of now. We don't have any change in deformation. We are seeing it from perspective where you don't see much changes in crosshead displacement as of now because it's very minimal and not really visible if you see it at this scale. So at this point,
And the displacement is only 0.4 inches, and the load value is 6,000 pounds. Wow, that's a lot.
that's a lot really. And at this point, we will probably start seeing necking in a short while, in which you can see a significant change.
Well,
in
if the specimen
deformation.
fails, right, my bet is this won't fail.
Well, what do you think are chances that this failure might occur, silently or loudly? What do you think?
When materials fail, they will have to release all the energy, right? And that
talking
energy
about-
can be sound energy or recoil energy or maybe heat.
That brings me down to the fact that there are a lot of other forms of energy that have been stored when you're growing the specimen.
Oh, yes, that's true. So, see, the value of the load is not decreasing, right?
It's almost a lot of it 7,000, but there is still no
So, Ed,
change
your bet is a failure.
Yeah.
because it's starting to stall and now it's starting to fall.
Oh, really?
Well,
Yeah.
Oh, you're right. So,
It's decreasing now at 69.70. Now it's going down.
so we just passed the ultimate strength point. And
now
while we were performing, we saw the necking, but in the video we cannot really see the necking, but the necking was prominent at this point. So let me go near the specimen and show that.
and then you can see clearly how the necking, well, it has just begun. You can see the diameter of the cross section at the central point decreasing slowly, and the value at that point is about 6,700, 500. The value is decreasing a lot at this point, and you can see the necking has already started. You can observe that the crosshead displacement is increasing, but the load is decreasing. So at this point,
Oh, that is some
Get ready.
prominent necking, huh?
for a bang. Here you go. The specimen.
That is loud.
Indeed, it
Let's
releases a
look
lot
at
of
the-
energy.
Oh yes, and let's look at the failure shape. It's a cup and cone type of failure.
Yeah, different materials will have different temperatures when you doing these experiments, for sure.
This experiment, we're not bothered about temperature yet, but just to let you know, you shouldn't touch it at that point.
And also
Yeah.
there was a message on the setup. Crosshead is about to return to its initial position. But before clicking on OK, he removed the specimens. Why did he do that?
This is so when if you hit OK, the jaws will move back to its initial position, and your sample could crash into each other, two
Oh.
ends, and if it crashes, this could damage multiple parts of your instrument. So this would be very important to remove your sample.
Here you see a classic stress strain curve, all the points that are of interest.
We can
And-
talk about the stress strain curve for a longer time,
No,
right?
we won't.
Yeah.
Oh.
So
yeah.
So here you can see the strained sample and a sample, the difference in length. Notice how one is significantly longer than the other one, and also thinner at the gauge section. And here's just a good comparison between the two.
Oh, so now he's measuring the final gauge length and the diameter.
And we can see how the differences are in the length of a deformed and the original shape. And that'll give you an idea how this material behaved when it was under tension. So we are measuring the two ends, and that'll give us an information about the strain that it had experienced. The curve will give us an information about the stresses that it had experienced. So in all, we have all the material parameters that are needed to ensure that we have the right information about the material. What do you say?
Oh yes, I totally agree. And now he's saving the data of the specimen, and this is really important. So we need to go to File, Export Preview, click on Specimen, and then this Notepad file opened up, and we saw that there are different columns and each of them is like load data, strain data, and so on. And now he is saving the notepad file in his folder, which we can send to the students or we can analyze the data, right?
Yeah, and they need to work on the tasks after that. So this is your file that you need to work on, and you have seen the experiment